Okay, we're recording now. So, hi everyone. Okay, I want to show two constructions of signatures from RSA permutation. So, actually, from any trapdoor permutation, but then specifically from RSA one. And trapdoor permutation and RSA trapdoor permutation to signatures. And first, in random oracle model for hash functions, and secondly, in the standard model. So without funny assumptions of this type, just assuming collision-resistant hash. First of all, I want to mention that in Katz-Lendl, you have the Goldwasser-Mikali reversed construction plus people afterwards, in particular Goldreich, which so this is tree-based construction, which uses one-time signature from which is implied just by one-way function, and a tricky way of chaining them. So from a one-way function, you can get a one-time signature. It's not a hard construction, but you, in order to sign an n-bit message, you basically, this is how you do one-time signature using just one-way function. You take, if you want to sign an n-bit message, you take n random points in the domain of a one-way function that will represent 0 bits of this message. And you apply one-way function. So you give the images, this is your public key, the images of the endpoints, which corresponds to n 0 bits. And likewise, you the n bits of the message can also be 1. So you pick another n points in the domain of a one-way function, you apply the one-way function, the outputs are n values in the range. These will represent bits 1 of the message. And the public key is the 2n values from the range. And how do you do a one-time signature? You just give pre-image of the one-way function corresponds to either 0 bit or a 1 bit, 0 bit or a 1 bit, depending on the bits of the message. Everybody can verify the signature because given the pre-images, you can map forward, but you cannot forge any other signature, right? And on other message, because that would mean inverting some point in the domain or range of the one-way function that you don't have the pre-image for. Okay, so that's a very easy thing. The question is, how do you chain them so that to be able to sign again? And the idea is fairly simple. Using collision-resistant hash, what you do every time you sign, what you do, you don't have to sign n-bit messages. Let's say that you have a hash onto n bits. You take your message and you create a new one-time key. Again, 2n elements from the domain of the one-way function. You apply the one-way function to all of them. the 2n vector of values in the range is the new public key. You hash the message with the new public key, that's your n bits, and that's what you sign using the current public key of a one-time signatures key. So what you get is a stateful signature. Every time a public key changes, and in order to verify a signature, you have to look at the chain of the public keys to the original one. Okay, so not super efficient and stateful. The trick is how to make it stateless. I mean, actually, it is not stateless, but how to make it at least, well, constant size, so it does not keep growing. So there is a lot of algorithmic ideas to, the basic idea. Okay, I just told you, and so read here. Okay, and okay. But no, so you can trapdoor permutations are in particular one-way functions, right? So you can use this classic result and the improvements on it, but it does not escape the fact that a signature is going to be n pre-images of a one-way function. So if you have any one-way function, okay, it has at least 160 bits or so, and then if n is a range of a hash function, then it has at least 160 bits, so it's 160 square. Okay, that's how long a signature is. So that's way longer than RSA signatures or bilinear map signatures, which are just, they could be as short as 160 bits, or in the case of RSA, 1000 bits, but still that's orders of magnitude less than stuff that comes from this beautiful generic results which show that it is possible under any one-way function, and also in the end, the algorithmic result assumes the collision resistance as well. Okay, so let's go to these. So so part one, assuming random oracle model, there is the so-called full domain hash version RSA. Okay, so I will, but actually any TDP works. Okay, so I will just use the RSA, and you can generalize it to any type of permutation. Okay, so what's the full domain hash signature, and it's abbreviated FDH RSA. So assume you have a random oracle hash H that takes any bits and outputs. It's a hash function that hashes onto the RSA domain. So this is the domain of RSA TDP. Okay. How do you construct such a hash function? Because these are numbers which are coprime with an RSA modulus. Okay, so given standard hash H prime that takes any bits into, let's say, a security parameter worth of bits, right? So like in the case of SHA, this is 100. Well, SHA-256 is 256 bits. And this is, at least 2048, right, or more. So So for example, you can implement it like this. H of x is h prime of x, say 1 x concatenated with h prime 2x concatenated with dot 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 h prime nx, where n is about the length of the modulus that you need divided by how big each of these chunks are, and add yourself a security parameter worth of bits. And the reason is that if you model H prime as a random oracle, so this is a random 160 bits, let's say 1160. This is another random 160 bits for every x, and so forth. I want the result to be uniformly distributed mod n. N is not an exact multiple of 2, right? But it's not an exact multiple of 160, of 2 to the 160. So I add sort of an overhang of random 160 bits, and I take all of this and compute it mod n, right? So because I started with a number that is at least security parameter more randomness than, it's an integer that is so the point is to make the result of this reduction uniform in mod n. You have to start with something that is a random integer that is significantly longer than n. Okay, and then the statistical difference between this output and random in the n will be 2 to the minus security parameter. Okay, so H is a hash onto Zn, not Zn star, but a probability that you find x such that GCD xn is not equal to 1 is negligible unless factoring is right, because if you hash onto Zn, and let's say you found a number that is not in here. Okay, so what is this integer? It's an integer that is not coprime with n. Okay, but therefore it's a factor of n, and therefore you can factor. Okay. All right, so you have this hash function, and now signature under the signature on M is a sigma such that sigma to the E is a hash of M. Remember last time, compare to textbook RSA. Where sigma was such that sigma to the E was just M itself. Okay. There were at least two issues. Issue number one is why this is not a secure signature scheme. Because under the assumption that RSA is hard to invert function, that assumption says if you give me a random element in the function range, then it's hard to compute the pre-image, the eth root of an element. Okay, But that doesn't tell me that an efficient adversary cannot pick some element for which it knows the pre-image. In fact, it's a trivial thing to do. He picks the image, computes the function forward, and that's a value for which it does know the pre-image. Compared here, the same attack doesn't quite work. Adversary can pick sigma, compute the function forward, but now he needs to find an M which hashes onto that value. If H is a random oracle, then that's like I compute some image, and now I need to query the random oracle on points, hoping that the value that the random hash outputs equals this one. If hash is a random oracle, that of course happens with negligible probability if this domain is large enough, and it is. Okay, so here is one reason for this hash, and one reason for when assumption that a hash is like a random oracle is incredibly convenient here. The second type of attacks had to do with malleability of this function. Okay, so instead of computing the pre-image and computing the function forward and getting the value, let's say that somebody else, a signature oracle, computed a pre-image on some message of my choice. Let's say it was this. So I chose a message, hashed it, gave it to the oracle, this message, and it computed the signature oracle from computed the pre-image. Can I now use the pre-image of my message to compute a pre-image of a different message? In here, it was possible because of homomorphism of exponents of the RSA function, right? If you have pre-image of some message and then a pre-image of another message, these two combined give you the pre-image of a new message. But is it the same here? Well, no, right? Because if sigma 1 is a hash of M1 and sigma 2 is a hash of M2, sigma 2 to the E, then if I multiply them, right, all I get is a hash of M1 times hash of M2, and I would be successful if this was hash of, say, M1 times M2, but of course, if H is a random oracle, these correlations are unlikely to hold. The resolution is not very good, is it? Okay, now it's better, right?
It's great.
Oh, okay, thank you. Okay. Okay. So that introduction of the hash also breaks this homomorphism. Okay. So intuitively, okay, it takes care of this one attack. It seems to take care of the other attack, but is it secure? I mean, just because it takes care of these two attacks, perhaps there is another one. So so we have we'll argue the following, that in general it's a sigma such that the trapdoor permutation applied to sigma is the hash of the message. So the first theorem is that for any trapdoor permutation F, system, right? Like in particular RSA, the FGH signature is CMA secure in a random oracle model for hash H. Okay, where hash H has to go, hit be uniform over the domain of, or rather the range of the trapdoor permutation, which in RSA case, domain and range are the same. Okay, so okay, so let's do this proof. Okay, so we'll do this for the case of RSA, and you can see that where it generalizes. So an adversary gets a public key, an RSA public key, right? And it can ask a signature oracle. Let's note it's sigma for signature on any message. It gets back a value, the signature, which has to satisfy the following equation. It has to be an ETH root of the hash of this message mod n. And the verification is sufficient. I take this to the E, and it has to be the hash. And after however many of these signature queries, adversary outputs m star sigma star such that m star is not equal to any of these messages that were signed, and sigma star is an ETH root of this hash. Okay, so what is happening here? Hash is a random oracle. So every time adversary sends some message to be signed, a message defines a random point in the domain, and what he gets is the ETH root of that random point. And then when he forges, he specifies some other random point, and it is random because a hash function gives basically samples random elements from the domain. And he's able to compute the ETH root of that point. What we would like is, our goal is to construct reduction such that R given n, e, and some random point A, for A random in the domain, such that this reduction reduction R, such that outputs the ETH root of the challenge point. So in other words, so this reduction would break the RSA assumption, right? Gets a random RSA public key, a random point from the domain, and it inverts the RSA function on this point in the domain. And reduction where R can interact with A, right? So it's somehow existence of this attack algorithm should allow existence of this reduction. Okay, so we can denote it like this. Okay, R is allowed to talk to algorithm algorithm A. So let's try to see how such a reduction could work, right? So reduction gets N, E, and A. Okay, and its goal is to compute the root of such that Z to the E is A model. Well, it interacts with algorithm A, and clearly, let's do the obvious. It gives to the A the same challenge public key that it has. So it must somehow emulate the signature oracle, right? Be able to sign these messages, no matter what they are, and it should make use of this forgery in order to translate it into solving the RSA challenge on point A. So, well, how can it possibly perform these signatures without breaking the RSA assumption right there? Well, the trapdoor that allows R for issuing these signatures is the fact that the hash function is a random hash function. So it's the reduction that will emulate the hash function. So when our adversary sends a message to be hashed, it's the reduction which will perform this hashing. So it will somehow define a hash of this message. That's because we are proving security in the random oracle model for the hash function, the theorem really says that there is no efficient algorithm A which breaks this while interacting with hash function H, which is a random oracle, and therefore the probability in the attack goes over the random choices of H. So what's the counterpoint of the counterpositive of that? Is the existence of an attack which succeeds while talking to a random function H in the sky, and the probability that the attack succeeds goes over randomness of the point, randomness of the key, randomness of this adversary, signature is deterministic, and the randomness of H. So the reduction the randomness in NE is the randomness of the challenge, and the reduction will implement H in such a way that these points look random. But how exactly they are chosen, it's up to the reduction. They just need to be random in the domain Dn star. So here is a simple idea for how the reduction can use this trapdoor. So whenever A sends mi to sigma to be signed, assume A first sends mi to H. Okay, so let's assume that whenever A wants to sign something, it first hashes it. let's write it as an assumption, and likewise A sends M star to H before outputting forgery. Why can we assume this? Because let's say that this attacker exists, okay, that survives this and creates a valid forgery. Let's now build a generic wrapper around this attacker, an A prime. A prime does this. Whenever MI is sent to signature, A prime checks, was it hashed before? And if it wasn't, it first sends it to a hash and then passes. Likewise here, if M star was not hashed, A prime will hash it. A prime has exactly the same probability of winning as A, right? There is nothing, A prime doesn't hurt A. So without loss of generality, you can assume that an attacker does that. Okay, then given this assumption, the idea for the reduction is whenever A sends M to H, let R take first sigma M as random in Zn star in the domain of the trapdoor permutation, and set HM to be the compute the permutation forward. Okay, so this is the trapdoor permutation on this point. Then clearly, this would mean that when A sends M to sigma, R can sign it, right? Because if H of M, which is the hash of M, is set to be this value, then clearly the reduction does have a value which is ETH root of the hash. This value is simply this, sigma M. Right? So sigma M is the signature on M. Problem. So good. So this reduction, without knowing any trapdoors, I mean, with just given the public keys, right? Basically embeds trapdoors into every hash function output, so that it can sign, quote unquote, them the corresponding messages. The problem is that when A sends M star sigma star, R doesn't learn anything. Doesn't learn anything new, right? Because sigma star is just sigma of M star. If everything is hashed using this method, then in particular, so is M star. So the reduction knows the pre-image of HM, of HM star. Yes, in this trapdoor permutation. So this pre-image that adversary creates is nothing new. The problem is that assume adversary first hashes everything. That's sort of the worst case here. Adversary performs billions of hashes. And then he signs some of them. He wants some of them to be signed. Some of the hashed message to be signed. Okay, the reduction is fine. And one of them he forges on. How can the reduction know which one it will be signed and which one it will be forged? but the good thing is, of course, the reduction doesn't have to know. So R can guess some J, J query to H, such that A will forge on MJ. Well, on the message in that J query. So, okay, let QH be the number of H queries A makes, and let QS be the number of signature queries A makes, and both are polynomial in the security parameter, right? Because adversary is efficient, so there's only polynomially many signatures issued and polynomially many hashes that the attacker can make. So this guess will be correct with the probability 1 over QH, which is 1 over polynomial. Okay. So he guesses this J query, and on J query to H, R sets HM to A, the RSA challenge of R, right? So reduction has to compute ETH root of this challenge value A. If the reduction sets hash of M on the J query to H to this challenge, then, and if this guess is correct, then sigma star is the ETH root of hash of, if this message M star is the J's message here, then sigma star is the ETH root of this value here, which is A. So reduction, then R can set Z to be sigma star if M star is equal to J's query to H. Questions on how this works? Are you still with me?
Professor?
Yes.
So in the RSA case, the signatures are uniform, but how about other TDPs?
So we need the TDP to be a bijection.
Okay. Mm-hmm.
Okay. So that's in the name. It's a permutation. It's a trapdoor permutation. Okay. So actually trapdoor permutation is like so literally it's the domain and the range are the same, and it's a permutation. So if you pick random elements in this procedure in the domain, then the permutation basically samples random elements in the range, right?
Right.
But so it doesn't have to be a permutation, it has to be a one-to-one, it has to be a bijection. But yeah, good point. Okay, so what's the probability that this guy that R succeeds? If epsilon is the probability that A succeeds, then let's call it EA. Okay, it's the probability that an attacker forges. Then ER, which is the probability that R succeeds, is at least EA times the probability. Well, there is two events that make, I should have first stated them clearly. Okay. So this is a little bit, okay. Sorry, so let me state these events. Two bad events for reduction R. Let bad one be the event that, well, how about if this guess is wrong, right? Well, you know what? Actually, there's one more bad event. So just for consistency with my notes, I want to name this bad event the same way I have in the notes. So my first bad event is that the reduction embedded this RSA challenge into this JS query to the hash. What if that adversary actually sends that JS query M into signing? Then the reduction has to solve the RSA challenge on A, right? Because this signature would be the ETH root of the hash, and the hash was set to A by the reduction. So the bad event one is that A sends you know what? Let me call this JS query to M, call it M bar. Okay. Once the reduction guessed some index J, then there is a unique message that A sends, on the JS query to the hash. Let's call it M bar. So the bad event is that A sends M bar to the signature oracle, right? Then R is stuck, cannot sign that. Okay. And the second bad event is the maybe the more obvious one. A sends outputs M star, which is different from M bar, as forgery, right? And all the forgery on all other messages is useless because reduction knows ETH root of the corresponding hashes. The only useful forgery is the one that corresponds to the JS hash, namely M hat. Okay, so what are the probabilities of these two? So therefore, the reduction succeeds with the probability that these two events don't happen. Okay, and they are independent. Are they independent? Well, I could probably substitute it with just upper bound the probability that either of them happens with the union of bad and the other. The point is though that so this is EA. What's the probability that bad one does not happen. It's 1 minus 1 over QS. Yeah, okay, it's bounded like this, right? No. So, okay, I have this fixed query here, which I want to be the adversary to avoid. First of all, he doesn't know what index J is. Why doesn't he know? Because HMs created in this way are random in Zn star, and A, the challenge is also random in Zn star. So therefore, this is always random in Zn star, regardless whether he follows this way or this way. So therefore, the index J is unknown to A. So what's the probability that one of these signed things matches index J? It is QS this is some trivial thing, and I'm losing track on what it is. You know, it is definitely upper bounded by this one, right? By 1 over QS. Because let's say that QS is larger than QH. So he will, no.
Isn't that a bound for bad too?
No. So, okay. What is the probability that bad one happens? Bad one is that one of these is this J. I used a simple calculation here, and I'm afraid this might not be correct. So when okay, so nothing stops adversary from taking all the hashed messages and signing them, except when we assume that he hashes all messages, including the forgery. So if he asked for signatures on all messages, on all hashed messages, then he couldn't forge because he would already see signatures on all hashed messages, right? So he has to pick at least one that he doesn't sign. And you know what? This is let's upper bound this. So okay. So definitely the reduction has some chance of succeeding, right? Because this forgery, so adversary has to, you know, the worst case is that he signs all of them except one. Okay. So let's just reason like this. Worst case, A sends all hashed messages to R except one, which is the M star that he uses in forgery. Okay, and let's just call this let's call the event bad, which is that M hat is in the set of sends all has messages to to sigma, right? So in the set of messages, A sends to sigma. Yeah, okay. Actually, it's not clear that this is the worst case. Yes, so he can still, yeah, because under this case, the M star is guaranteed to be the correct one once you avoid this. Yeah, so the true analysis is really bed 1 and bed 2. So we have to assume that QH is larger than QS, right? You cannot sign all the messages that are hashed. So therefore, probability of this event so there is a set of hashed messages, and inside of them there is a set of messages that were sent to the signature, and we are hoping for M hat to be in this set. And so the probability if M hat is chosen in this set at random, right? So this set has QH messages, and this set inside has QS messages. So what's the probability that it falls into the wrong set? It is QS over QH. Okay, and the probability of event bet 2 is what was bet 2 is that M star is just, we are unlucky here. So that's no, at most 1 over QH. Okay, and so let's look at this probability. Oh, no. Probability of bet 2 is unfortunately, at most 1. Okay, is I can only upper bound it like this, right? So I mean, perhaps I can upper bound it better, but okay. So the complements are 1 minus QS over QH, and complement here is just 1 over QH. Okay, and so this is, if I upper bounded using this method, okay, then I get doubly bad results, because this I can only upper bound as epsilon A 1 minus QS over QH times 1 over QH, and so in practice this is close to 1, okay, because number of signatures is always much smaller than the number of possible hashes. Hash is a cheap local operation. Signature involves interaction with a good, with a challenge, with an honest party that signs. So we can always assume that the number of signatures is dwarfed by number of hash queries, in which case this is a small value, and you can approximate it as 1 or 1/2. Anyway, it's a constant and close to 1. So it's this value that truly matters. Okay, and this is something we call security degradation. And why? Okay, so first, this is we proved what we were after. If epsilon A is non-negligible, then this is non-negligible divided by a polynomial, which remains non-negligible, and so reduction succeeds with non-negligible probability. Okay, so in terms of asymptotics, you do break the RSA assumption if this attack existed. But in terms of exact security, it's not that great, because let's say that you have an attack that succeeds against some RSA scheme with a probability 2 to the minus 50. Now, it is okay to assume that a realistic algorithm can perform 2 to the 50 hashes. So hold on, epsilon. Okay, so the maybe easier way to think of security degradation is the other way. So assume take RSA parameters where best attacks are approximately would succeed. Best feasible attacks would succeed with probability say 2 to the minus 80. Okay, then that means that R that there can be no R such that ER is greater, reaches the 2 to the minus AD point. And what does this imply against security of a signature scheme? So what it implies that EA must be smaller or equal to ER times, let's ignore this because it's close to 1, times QH. Now, realistically, QH could be 2 to the 50, okay, or even more. So this value is only 2 to the minus times 80 times 2 to the 50, so it's only 2 to the minus 30. Now, this is not a great bound. Okay, it's if there is a billion people using this scheme, then for one of them, attack will succeed. Okay, so this is not a great bound. In asymptotically, it works. If you plug in concrete numbers, it works less well. So where was the where is the issue? Well, that we in this reduction, we have the reduction have been embedded the challenge value into a single hash query, whereas all the remaining hash queries, it prepared itself, it embedded trapdoors to be able to sign. The reduction could work better than that. It could have a different strategy where instead of guessing a single query, it guesses some fraction of queries in which it embeds this challenge into hashes for all of them. Okay, but how? And okay, if it managed to do so, then probability of bad event 1 increases. We have no longer just a single query that the reduction is unable to sign. There is a whole bunch of them. Yes, a whole fraction. And so there is a set of hashed values. There is some fraction of embedded into the hash, and then there is a fraction of them which are going to be sent to the signature oracle. The bad event is for these two sets to intersect. Since realistically QS is much smaller value than QH, so you're going to think of this as 2 to the 30, and this whole thing is, like, say, 2 to the 50. The reduction can still succeed even if the set is much larger than a singleton. And what it does is that it pushes, it increases bad 1, but it decreases probability of bad 2, right? It's now no longer a single forgery that works, but a whole group of them. Okay, so but how can a reduction embed this RSA challenge into many hash queries if it simply sets many hash queries to this value, then that's clearly incorrect, because this is supposed to be a random oracle. So at every point, it outputs a random point in Z and star. They cannot be that attacker hashes a whole bunch and they all collide. Okay, then clearly attacker will immediately recognize that he's not interacting with a hash function. He's interacting with some BS algorithm that tries to cheat him, right? I mean, so okay, attacker is an algorithm. It doesn't, it's not like supposed to detect hash cheating. But the point is, attacker was some algorithm that worked in specified way, given that the hash was random. If this hash is not random, you have no idea what this attacker does. In particular, it might not forge. Okay, so reduction has to supply attacker with the same distribution that attacker sees in the real world. Okay, so how does this embedding can work? So better reduction if so this is idea 3. Okay, if the TDP is homomorphic, like the RSA TDP, okay, then R can embed A into many H query outputs. Okay, how? Pick a random long enough integer alpha. So at J's query to H, pick long enough integer, let's call it alpha J, and let's call this query MJ, and set H of MJ as A to okay, let me as A times G to alpha J E for I guess it doesn't have to be no, sorry, random alpha J in Z and star, and pick it H as A times alpha J to the E. Then. Okay. Then, if A outputs any such MJ as M star forgery, then R outputs B as sigma star times divided by alpha J mod n. And note so this is the modified reduction. Okay, it's modified right in this point, right? Instead of choosing a single query, it can now embed into many. and it embeds this way rather than simply setting the single HM to A. Okay, and so why does this work? Because note B to the E is what? It's sigma star over alpha j to the E. And if so, sigma, so this is sigma star to the E times divided by alpha j to the E. But sigma star to the E is supposed to be hash of M star, right? So if sigma star is a forgery, output, right? And sigma star is a forgery on M star, right? So sigma star to the E is hash of M star. So this is divided by Lj to the E. And hash of M star is if M star is equal to Mj, then this hash is hash of Mj, right? And hash of Mj is A alpha j to the E, and if I divide alpha j to the E, I get A, right? So B is the pre-image of the challenge point. What reduction did is it took a challenge point and it embedded it into a random, embedded this challenge into a random point in the domain by shifting the range element by a trapdoor permutation applied to a random domain point. This is the homomorphism that was used. It's the same homomorphism that was used here, right? I had A is a value of the TDP on some point sigma, which I want to find. This is my point B. That is my challenge. I want to find it. But instead of embedding, just giving A as a challenge to the attacker by embedding A into this hash right here, right? I embedded using this randomization. So I take the random point I'm given, and I compute my own point, sigma 2, this is Lj, compute the function forward, this is M2, and I give the product as HM. Now, if somebody inverts the RSA function on this product, then I basically get the product of the preimages. But I knew this one preimage, so I just need to divide it out to get the other preimage, and that's exactly what I'm doing. Right? I take the preimage of the product that the adversary gave me, divide it by the preimage that I picked, and I get the other preimage, which is the preimage of the challenge A. It only worked if the trapdoor permutation is homomorphic. If not for this property, I wouldn't be able to randomize a challenge point and create a random new point whose inversion allows me to invert the original point. Why was I able to do so? Because now look, because it's a randomized embedding. At every query, I pick a random alpha j. RSA is a permutation, so this is a random point in the domain in range. So A is fixed throughout the reduction, right? But each of these HMs created in this way is random because alpha j the trapdoor that the reduction embedded into each of these was random in Z and star every point at every time. So these HMJs are also random in Z and star. Okay, so again, that reduction succeeds right here. The rest is the more exact analysis of the bad probability of the two events. Now, right, when the probability of bad one increases, because now this is a bigger set, but bad two decreases. So I basically balance these two, and I don't use the product. I upper bounded, but I should already here. I should have upper bounded them by the sum, right? So roughly, I can pick a security parameter, a probability, with which at every query here, with some probability, I throw this query into this set, so I embed the challenge, or I throw it outside, so I embed the standard way, so I can quote unquote sign, and then I have to just adjust this parameter so that these two probabilities have roughly equal sizes, rather than being so unbalanced as in here. And this randomization allows me to reduce the degradation to just 1 over QS, which is much better in practice because number of signatures is usually much smaller. So in any realistic systems, people don't sign that much. Okay, they don't even sign 1 million messages. They probably don't sign, okay, so they upgrade keys. They don't use the same key over and over. So whereas the number of hashes can be like 2 to the 50, number of signatures is more like 2 to the 20 or 2 to the 30, at most. So I have improved the exact security quite a bit. The point of the story is, okay, there is some value in these exact security improvements, right? It's the better implication in practice. But also it is to show that, this simple reduction idea where I embed trapdoors, which either allow me to sign or it will allow me to extract an answer to the challenge from a forgery. I can do so probabilistically, and I can balance out so that to make the probabilities of failure on both sides roughly equal, and maximize the probability that the reduction works. And a very nice, I believe, okay, I hope you agree, technical point is that the same technical property of homomorphism that basically messes up the textbook RSA construction, in a way, surprisingly, comes up and actually helps the reduction. Without this homomorphism, it would be not know how to embed the same challenge in multiple points and use the forgery on any of them to solve the original challenge. So this double-edged sword of homomorphism of nice algebraic properties can work against us, but if we work a little harder, it might work with us. We might utilize it to enable reductions. Okay, this is not a dramatic thing because we already had a reduction, it's just had a much worse security degradation. But in many cases, this will actually be, a night and day from totally being unable to reason about security at all to actually being able to. Okay. So originally I was, hoping that I will do 2 parts with this first random oracles and a standard model. Of course, I basically spent the whole lecture on just this part, but that's okay too. Okay. Let me know if you have, if I can answer any questions on this.
I have a quick question.
Mm-hmm.
So before the homomorphic part, nothing that we did required groups, right? That's the first.
Say this again.
We didn't use groups at all before, right? Only in idea 3. Like everything would work for a TDP from some set to some set, the same set.
Yes. Yes. Okay. Yes. So the first reduction worked regardless, and only here we use specific properties of RSA. Exactly. Okay. The strength of the random oracle, right? Is sort of, it's really amazing because it allows the reduction to perform all sorts of trickeries, embed challenges into some hashes, embed, right? And embed trapdoors that allow signing in other hashes. It is almost like a cheat. It seems too easy. Maybe you disagree, but if we don't have such flexible objects which a reduction can take over and then embed whatever it pleases in it, okay, as long as it has correct distribution, these reductions would be definitely harder, right? So I do want to show next time how you can do this in a standard model. Okay, you pay for it. It's slightly less efficient, but it's still educational to see how you would structure such arguments. Of course, there's many arguments of this nature, right, that appear in cryptography, in any context. So let's just see them in the context of RSA-like signatures. Okay, so I'll see you next time. I'll post some links to papers, if you want to read up. But we'll just go over one of them next time. Okay, thank you.